Hello everyone, I would like to welcome you all to this lecture of today. First we will look at what we did last time in a very brief manner. Towards the end I introduced the Fleming Tamao oxidation and discussed the oxidation of carbon silicon bond to the corresponding carbon OH bond, where we discussed the mechanism of the Fleming condition based oxidation. So, what we had discussed last time was that if one has a substrate of this type where we have a phenyl ring attached and there are two groups which are attached here, and of course you have the substrate on which we have say here we put it R1, and this is the if we put it as R2 here and this as R3, then we have the asymmetric center here. And what we discussed was that in the presence of potassium bromide per acetic acid like this and acetic acid as a solvent, one can convert the substrate to the corresponding alcohol with the retention of the stereochemistry here. What we did was proto desilylation, and we proceeded via the corresponding halide which is present on the silicon, where you have the phenyl ring was replaced by X, which is like a bromine, and then of course we went further. So, there was this conversion of this silicon substrate to the corresponding silicon halide substrate, and then we did the oxidation with the per acid here. Say you had CH3 CO3H, which underwent somewhat like Baeyer-Villiger oxidation type of substrate, and finally basic workup followed by protonation led to the corresponding alcohol like this here. So, we will see now how this two step process can also be done in a slightly different way, and how modifications have been done to get one step or one pot operation. So, this two pot operation which I showed where a substrate of this kind was reacted with potassium bromide and peracetic acid. But one can also use somewhat different reagent systems such as HBF4 fluoroboric acid or BF3 etherate and acetic acid combination, and these act as source of proton as well as F minus as a nucleophile. So, instead of getting what we saw last time, instead of getting here, instead of getting silicon and bromide, what we saw the last time, instead of bromide, now what you will get is fluoride, because it HBF4 as well as BF3 acetic acid is a source of F minus. So, instead of getting this bromide, one gets fluoride, and then one can use in presence of any para acid such as metachloroperbenzoic acid, one can use triethylamine as a base or potassium fluoride as a base. So, one can then convert that silicon fluoride based intermediate to the corresponding alcohol, similar to the mechanism that we discussed using Baeyer-Williger type of oxidation. Now, they also invented a one pot operation here. In the one pot operation, what they have done is that they start with the similar substrate of the silicon type, and now they use, say for example, mercuric acetate as a reagent in presence of peracetic acid and acetic acid. So, or one can also use bromine, molecular bromine or potassium bromide and peracetic acid also, but it is a one step operation. That means the intermediate which is formed like this, which is going to be say somewhat like this. The electrophile attaches to this particular carbon atom of the aromatic ring, and the positive charge is formed here. Now, it is very clear that this bond has to break and you regain the aromaticity. In the process, this silicon is attached by the para acid that one uses. Say for example, here you have CH3 CO3H. So, your para acid attacks onto this silicon in the same pot, leading to the corresponding intermediate which is expected to undergo the rearrangement of which I termed as Baeyer-Williger type of oxidation. So, this is the substrate that one can directly get under these conditions, where any electrophile such as mercury plus or Br plus in the acetic acid and peracetic acid medium can directly give this one. So, this is an advantage of using a one pot operation rather than isolating, but then there are both the options which are present and can be utilized, or both the protocols can be utilized. So, as I said, the electrophile reacts with the benzene, and now your nucleophile can directly attack on this one, and this particular X is not a halide, not bromide or any other halide, not bromide ion or bromine, but it is as I explained earlier, that directly the electrophile allows the acid, the peracid, to react to form this substrate, and which undergoes oxidation eventually to form the corresponding alcohol. Now, what is the evidence for retention of stereochemistry in Tamao-Fleming oxidation? The evidence was provided by a set of experiments that Tamao reported. What he did was he started with a silicon containing moiety like this, which is a bicyclic bridged molecule, in which he had the carbon silicon bond in an exo oriented fashion. Of course, there will be substituents as somehow used on silicon like this. Then he carried out the oxidation under his Tamao oxidation condition. Then what he obtained was the exo alcohol, which was 100% exo. In a similar fashion, when he started with another molecule in which the silicon now was endo-oriented, this particular compound had 95% silicon in endo orientation. This particular molecule led to the formation of the endo product again in 95%, indicating that there is a 100% retention of the stereochemistry. This set of experiments clearly indicate that there is a retention of stereochemistry in Tamao-Fleming oxidation. Now in Tamao oxidation, the more reactive fluoro or chlorosilanes are used, in which silicon is a stronger Lewis acid and shows more metallic character than the substrates used in the Fleming oxidation. So you have a substrate like this, which is SiR2X, where X is chlorine, fluorine, hydrogen, OR, Nr2. These are the substrates, these are the groups which are used on silicon in while carrying out the Tamao type of oxidation, which I have not yet discussed in detail, but now we will do that. Now further activation by a fluoride ion then leads to a pentavalent intermediate, which is able to bind hydrogen peroxide. Now it is something like this. If one takes a silicon substrate which is having here shown as 3 chlorines, but one can also start with only one halogen. Then the fluoride ion is attached, is reacted with, which forms a pentavalent intermediate. This is a pentavalent intermediate, and then hydrogen peroxide also react with it to form the hexavalent silicate ion. So it is an example of hypervalency. So one can start with a tetravalent silicon going to pentavalent and then to hexavalent silicate ions, and then there is a transfer of the R group, which is what is supposedly a chiral group if one starts with a chiral substrate, to the corresponding oxygen which is attached to the silicon, and then there is a loss of OH minus and we get an intermediate of this type where oxygen is now attached to the silicon and the R group has been transferred onto the oxygen which is attached to the silicon. Then of course one has the hydrolysis to form the corresponding OH here. So this is the Tamao oxidation in which we have a slightly different requirements as far as the starting material is concerned, and of course one uses the fluoride ion. So if we start with a substrate of this kind here, for example, where the carbon silicon bond has a well defined stereochemistry, that is alpha orientation here with a, of course fluoride attached to the silicon, and under Tamao conditions which utilizes 30% hydrogen peroxide, potassium fluoride under basic conditions and using methanol or water as a solvent along with THF, then one directly gets the hydroxy compound with the retention of stereochemistry like this. It has been shown that in case when methanol is used as a solvent along with THF, then an intermediate of this kind where OR is nothing but O-methyl is obtained as an intermediate, or when water THF is used as a solvent system, then here OH group has been observed to be present, and this particular intermediate then under the same condition leads to the formation of this hydroxy compound, indicating that in these Tamao type of oxidations these type of intermediates are first formed. In the case of Fleming type of conditions, which is very different from Tamao condition, we of course have to have a phenyl group here, and we have now a well defined stereochemistry at this junction where carbon silicon bond is formed, and of course we have another well defined stereochemistry at the adjacent carbon atom. And under acidic conditions, when the reaction is carried out, there is a retention of stereochemistry of the hydroxy group in the final product. In a similar fashion, irrespective of the stereochemistry of this particular carbon carbon bond here, if this is alpha oriented, then of course, irrespective of the stereochemistry of this and this, whatever is the stereochemistry of the carbon silicon bond, that is what is translated into the final product. That means there is again retention of stereochemistry. So looking at these two examples, it is very clear that the stereochemistry on the next carbon atom here doesn't have any influence on this stereochemistry of the final product. That is, in the case of Tamao-Fleming oxidation, there is a retention of stereochemistry in the final product. Now there is a very interesting reaction that we would like to look at it, where this particular organosilane compound has been converted into a very useful dihydroxy molecule of this kind, which is a useful synthon in organic synthesis. Now this organosilane molecule has been prepared by reacting this hydroxy compound with the chlorosilane of this type under basic condition, and then allowed to undergo thermolysis at 190 degrees, whereby this undergoes cleavage, as I have shown here, to release this alpha beta unsaturated aldehyde. And since there is already an olefin present in the molecule, this undergoes a hetero-Diels order reaction, because we can consider this particular part as a heterodiene. And since the Diels order reaction is a concerted process, so this particular hetero-Diels order reaction leads to the formation of this particular bicyclic molecule with well-defined stereochemistry at the newly generated asymmetric center. Now, if we allow this bicyclic molecule in which there is a carbon silicon bond with a well-defined stereochemistry to undergo Tamao based oxidation under these conditions, then carbon silicon bond, which is beta oriented, leads to the formation of a carbon hydroxy bond, which is also beta oriented. That means with the retention of the stereochemistry. And this oxygen silicon bond under these conditions undergoes cleavage, leading to the formation of the corresponding diol. That means we have converted this very interesting starchy material into a very highly useful dihydroxy compound, which is a useful synthon in organic synthesis, by utilizing two reactions, namely hetero-Diels order reaction and Tamao oxidation. Now, if we take a substrate of this particular type, and if it is chiral molecule, that means optically pure molecule, then under Tamao oxidation conditions, we can convert this into the corresponding alcohol, which is optically pure, because the starting material is optically pure. And this particular starting material can be prepared from this olefin, which is an aromatic alkene, by enantioselective hydrosilylation, a process that has been described in this particular paper. Now we have substrates of this type, alkenyl silanes, which can under neutral or basic conditions which employ something like this. You have in neutral conditions hydrogen peroxide, then this KHF2, then you have DMF at room temperature to 60 degrees, then you have a basic conditions under which you use potassium bicarbonate and methanol at 60 degrees. Under these conditions, when a substrate of this type, which has one hydrogen present here, leads to the corresponding aldehyde. That means under these conditions what is formed is something of this type. So, this total alkenyl group is transferred to the oxygen, and then of course you get an OH, and which is nothing but an aldehyde, because this will come here and this will come here and it will form the corresponding aldehyde. But under the acidic conditions, if one takes hydrogen peroxide, acetic anhydride KHF2, which is now an acidic condition, in these acidic conditions one then gets the corresponding acid. So, what is observed is that if the substituents are like this on the silicon, then what is found is if just 2 equivalents of oxidant are used, 2 equivalents of oxidant are used on compounds with this type of substitutions on silicon under acidic conditions, then only carboxylic acids are observed to be formed. It indicates that alkenyl carbon silicon bond migrates preferentially. So, this is the migration, this is the alkenyl silicon bond that migrates to the oxygen of the oxidizing agent like hydrogen peroxide, then that forms an intermediate of this kind. Here the methyl silicon bond is not transferred or does not migrate. When the acid is used here, the hydrolysis will give the aldehyde by the same way as the earlier, and that forms the corresponding aldehyde, which again reacts with the oxidant to form like peracetic acid or hydrogen peroxide is added in this, one gets the oxidation to the corresponding acid. So, basically it indicates that under acidic conditions you have a slightly different, where you have the acetic anhydride that is used, that leads to the peracid here, and this is what the peracid is, and that undergoes oxidation of this type to form the acid. So, this alkenyl silanes are utilized to get to the corresponding aldehydes or to the acids, but of course if one starts with a substrate in which there are 2 substitutions here, this was mono substituted, and if it is a di substituted, then obviously you will get the alcohol coming like this, where carbon silicon bond is replaced by the carbon silicon bond is replaced by the carbon oxygen bond, and that leads to the corresponding diketone. So, under these conditions it does not matter what conditions are used, whether acidic, neutral or basic, you can only get the corresponding ketone. On the other hand, when the substrate is mono substituted in the sense that only one substituent is present as R, here there are 2 substituents present. Of course, silicon will be common in both the cases. So, in the case when there is a mono substitution, one can get the possibility of getting the corresponding acid if the acidic conditions are used. So, we will stop it at this stage today's lecture, and we will take up other oxidations in the next class. So, what I discussed today was basically this Tamao-Fleming oxidations mechanisms and their applications in different types of conversions, where you can convert an enantioselective carbon silicon bond or chiral carbon silicon bond to the corresponding chiral OH bond, and therefore you have a possibility of generating chiral molecules without any problem if you have a possibility of making the chiral carbon silicon substrates. So, you can go ahead and read the references that I gave or the material that I discussed carefully, and we will take up the other oxidations next time. Thank you.